systematic way of visiting all the nodes. Okay, all the nodes will be visited, but it might follow any order, any way. Any order can be followed from one to the other. Okay, so we are going to see about depth first and breadth first and depth first. So in breadth first search by the name, actually breadthwise, the searching is made by breadthwise, but we are going to use the concept called as, see, already I taught you in traversal, in tree traversal, I told you level order, right? Level order traversal. Level order means it is like breadthwise only. But that is just when we'll be seeing all the nodes in each level and we'll be printing it. We'll be traversing from the left to the right and we'll be printing. But this is different. Keep it in mind that breadth first search always uses a queue concept, and depth first search will be using a, so this will be using a queue concept, and this will be using a stack concept. Okay, so this is what we are going to follow. So even then, if the name is not given directly, find the traversal, or they'll give a diagram and they'll use implement the queue concept and find the traversal. So if they give like this, you should understand that it is breadth first search. Or apply the stack concept and find out the graph traversals of the below diagram, means that is your depth first search. Because for this both we will be, the algorithm uses queue concept, here it will use the stack concept. So in breadth first search, first we have to, the concept is similar. First you choose a source, any node. Maybe if they have not given any node, you can choose in the starting node as your source node. And when you start to visit that particular node, you have to mark it that it is visited. That means it is visited, or we have gone through the particular place. So if it is visited, means then from that particular node, you have to find out what are the other nearby vertices to it. So other nearby vertices you have to find first. That all the nearby vertices, whichever you have found, that everything you have to push into the queue now. Everything has to be pushed into the queue. The vertices which are found has to be pushed inside the queue. Once after pushing it into the queue, what you have to do is the first one, that is the first in first out, right? Queue. So the first one which has been pushed has to be taken out of the queue now. When that is being taken out, its corresponding nearby vertices has to be looked into. So when you looked into, that has to be again pushed in. So this will be following recursively. So I'll show you the problem. So you have to keep on repeating the steps again and again. So same thing, only in two different ways I have expressed the algorithm. So now see here. First I'll show you with a very simple example. So here there is no arrow marker, nothing. It is A, B, C, D. Okay. So first I will be starting from A as the source vertex, and mark it as visited. So A I have visited. So what I will do is, now my A is over here. Assume that my A is here. I have visited that node. Now its adjacent vertices B and C I will push into the queue. So I have pushed B and C inside the queue. Now what I will do is, A has been visited, so I have marked it separately. Now I will do the, when B and C is pushed, now I will be taking B out. That is, I'm going to dequeue it. So when you push the adjacent vertices, you can draw its corresponding diagram. Diagram also. Diagram in the sense you can draw like this. B and C are pushed inside the queue. So this is the way I represent. Otherwise, what I can do is the same way I will draw it. Okay. So B and C are the adjacent vertices. So I have drawn like this. B and C are the adjacent vertices. Now B is, I'm going to dequeue the B now out. So when I'm going to dequeue, once again I look into this graph. Actually, algorithm wise, you have to find out the adjacency matrix. These all I have taught you in the last class itself. A, B, C, D. Then again A, B, C, D will come here. Picture is having A to A, no connection. then A to B there is a connection 1. So based on whichever is having 1 will be the adjacency matrix. That is called as that only we will be doing it in the program, coding it in the program. But when I'm solving it manually, I can directly look into the graph also, is fine for me. Whichever is easy, you can follow. So when I have pushed B and C inside the queue when I have visited A. Now what I will do is, now B and C are inside the queue. Now I'm going to DQB. That means removing B. I'm going to remove the B. When I'm removing B, again I have to look into this graph. What are the adjacent vertices of B? So adjacent vertices are A, C and D. A is already visited, so I don't mind that. I will not take that once again. And C is the next one. C is already in the queue. So the next one is D, which is not in the queue. So I will take this out and I will push. Already C is there in the queue. D also I will insert. So from B only actually C and D are there. C is already in this diagram. So I will I will add only D to this. So this is so see, all my vertices are there. Otherwise, if I draw like a tree, I'll same diagram only, Matthew. I represented it like this. That's all. From B to when I'm DQing B, I have received D as the output, D as the adjacency matrix. So this is my BFS diagram. This is my BFS diagram, breadth first search diagram. A, B, C, D. This is the order. A, B, then C will come out, then D will come out. A, B, C, D. So both diagrams are same only. Now when I draw it as a Q diagram, when I draw it as a Q, first I will take B out. Then you see here in the next diagram. Then when I'm taking B is DQ'd, its adjacent vertex C and D are pushed in. Okay, since and C is already there in the queue. These are explanation you should make when you write it as a problem. So since C is already in the queue, vertex D alone will be DQ'd, NQ'd. Now next C is only in the queue. Now once again when C is there, I will look into the diagram. C's adjacency are A, B and D. But A, B and D are already A, B and D. Here it is. A, B and D are already in the A and B are visited and D is already in the queue. So there is no need of NQ operation. So now C is also taken out. Now again D is only left out. Until your queue becomes empty, you have to take all this one by one. So this is the diagram which I have drawn here. Okay. Now I will show you another example which can make you more clear. See, this is another example of breadth first search. Now look into this diagram. So A, B, C, D, E, F, G. Till G there is or the diagram, all the vertices. So how many? 1, 2, 3, 4, 5, 6, 7 vertices are there. Okay. My final diagram also should contain 7 vertices, provided edges will be less. Okay. Edges will be less. So that is the one, and it should not form a cycle also. So that also you should see. So now see here. First I'm starting with A. A has been pushed inside the queue now. Okay, and see here I have colored A also. I have colored A. A is being colored now. Now, when I'm going to take A out, that is I'm going to DQ A. When I'm going to DQ A, can anyone tell me what are the vertices which I push into the stack? Please tell me what are the vertices I have to push inside. Do I need to call by name?
Ma'am, B, D,
Sarat?
and E. Oh,
Huh?
sorry.
B?
B, D, and E.
Yeah, D, E, B. You can push it in any order. Okay. You can push either B, E, D or D, E, B or E, B, D. Whatever order you can push. Okay. The order is, no, the order can be anything. So in this diagram, actually they have pushed D, E and B. Okay. So D. So then immediately I'm marking it in the diagram you see. So whenever they give this diagram, first draw a empty nodes like this. A. If you need, you can draw, because needed things alone you can mark it. So this position itself you can draw A, B, then C. Then here is one diagram, yeah, that is G, and then D, E, F. Okay. So D, E and F. Okay, so I have drawn only the nodes as of now. Okay, so now what I will do, when I take push A into the Q, you need not draw anything now. Each steps is also needed. This will be mostly a 16 marks question. They are ask this problem solved in 16 marks, so the steps are very important. The See, in your fifth unit, all the problems are very easy to find out. When you look into the diagram itself, you will find out the answer, but steps carries marks, so you have to do with the steps only. Okay, when it is coming to a bigger problem, you have to do with steps. So A, B, C, D, E, F, G. So this I have drawn now. Now I have written the notes just like that. That's all. Now in step 1, what I'm doing, I'm pushing the A inside the Q. And now when I'm going to DQ it, I will find out the adjacent vertices. Adjacent vertices are, so that alone I will darken it now. A, so my diagram, first one. First connection from Bedford search. A, B, D. So D, E, B I have pushed inside the stack Q now. So when I'm pushing now which one has to be DQ'd? D has to be DQ'd now. This has to come out now. So when D has to be DQ'd, now I'll go into the diagram. I will check D's adjacent vertices are A and E only, right? Is it A and E?
Yes, ma'am.
Yes, ma'am.
These adjacent vertices are A and E. But A is already entered the queue and it is marked as visited. So what we have to do is, now we have to look whether E is there in the queue. E is already there in the queue. So there is nothing to push in this state. But you can mark in this diagram. What was the adjacent vertices of D? DE, but E is already marked over here, so don't put a line over here, already visited. And A is also already visited, so no need of any attachment diagrams or no need to push anything inside the queue. Okay, so now D has been DQ'd out. Now next one is E. When E has to be DQ'd, again I will look into this diagram. What are the adjacent vertices? E's adjacent vertices are B, A and C. A is already visited, B is already in the queue. Only the additional thing is, what is the additional adjacent vertices of E, which I have to enqueue it? See, you have to answer for each and every question, because then only otherwise I feel like that I'm teaching to myself.
Mom,
See,
C
when
and
I'm
F.
C and yeah, C and F. Okay, so E's adjacent vertices are C and F. It is B and A also, but A is already visited. B is also already visited. That's the meaning. Are already in the queue. Then only the thing which is not there is C and F. So I will include C and F over here. So now I will draw the connectivity. So when I'm dequeuing E, I have got new vertices C and F. So that I have joined now, and I will, when D is DQ'd, you can see the diagram. C and F are NQ'd. So when E is DQ'd, C and F are NQ'd into the Q. Okay, or entering into the Q. Okay, that diagram only I have attached here. Now, what is the next one left out, ma? Next, so E is also has gone out. Next one, B is only there. Now B, go and look into the B. B's adjacent vertex are A, C and E. A is already visited, C is already in the queue, and E is also already, A and E already visited. And only thing is C is not visited, but it is already in the queue. So there is no need of any updation. Okay. So now B is also taken out. Now the left out is C. So when C comes, now I am going to see what are the adjacent vertices of C. C, B is there, E is there, F is there, G is there. B is already visited. E is also already visited. And F is still in the queue. And only thing which is not there is only vertex which is not there. See, if you are not responding, I
Ma'am,
won't
G.
explain anything. Only thing is
G.
not G, because problems means please respond. It is not the thing that you can learn at the later stage, or anyway ma'am will post the recording at that time I can hear. That is different. But now as far as in the class you have to, otherwise I'll call by names. I'll call by names hereafter. Because hereafter all are problems only. The next question will be given to you only. So hereafter I'm going to call by names, and if you are not answering or responding, I have to mark you, even though you are in the class, inside the class. If you're not responding, absent will be marked, because I could see that same boys keeps on, boys or girls, anyone, same student keeps on giving the response, and others are still quiet. Don't do that. See, previous classes was algorithm, and it was a concept which was new. I was keeping on explaining that this is also new, but still the other steps you could interact and tell me out, so that it will be easy and good also. Okay. So what is the next vertex of C, which is not at all encountered into the Q?
G.
G. So G has to be pushed inside after F. So now I will draw the connection. C to C is on, when I'm visiting, when I'm dequeuing C only, I found out G is not visited. So there is a connection now. Now you could see that all are connected, but anyway, only final diagram I'll tell you. So C and C, so G is entering now. G has been entered now. Okay. Now the next one is F. When F is taken out, I will be finding out its adjacent vertex. F's adjacent is C, E, and G. So C is already visited in and gone, that is entered into the queue and gone out only, is marked as visited. Then E is also there, out. Now G is already in the queue. So there is nothing to enqueue inside my queue. So F is also taken. Now last one is G. So when I'm seeing G also, C and F are the vertex which is adjacent to G. But I could see that C is already entered in and taken out. F is also entered in and taken out. So when it is entered in and taken out, that will be marked as visited. So now I can take this G out. Finally, my Q should be empty, and my diagram, the same diagram here which I have drawn over here, this diagram is only in the last stage. You can see now. This diagram is only in this stage. Okay. So when I entered A, I found out what all the adjacent vertices, and I darkened B, E, and D. Then when I took, it was DEB. When I took D, A, E are the adjacent which is already there. When I took A, B, and C, C was C and F for the new one. So that alone I will draw it. Then when I took, then the next one was DEB, right? B was A and C, which is already visited. So I will not mark anything. I will not draw any line over there. Now comes C. Next is C and F. C, when I took C, I found out a new vertex. Whichever vertex which you are finding it out new and entering into the queue, that you have to darken it. Okay. So my final diagram will be like this. This is my final diagram. Without other connections, all will be left out. So this is my queue also should become empty. Stop the BFS process, and my spanning tree will be A, like this only. This is my spanning tree, my final diagram. So for this only you will be getting the marks at last. That is from this diagram or this diagram, I can tell you. This, from this entire diagram, I have found out the near this diagram using breadth first search. Using breadth first search or using the Q concept, I have found this diagram. Are you clear with this? Clear with BFS, students?
Yes, ma'am.
Yeah. So so my time complexity will be, you'll be learning it anyway in detail in your next semester, but I'll tell you how it is found alone. Basically, for all graph itself, your time complexity will be O of, based upon the edges and the vertices only you are going to express. Okay. As in, that is, otherwise you can tell it as O of the BD, breadth BD. That is, one is your edge and one is the vertices, B and D. Okay. Depth level and the number of children. That is what called as the edge and the vertices will be the number of this, and each where the edges follow. So you can represent. So for as of now, you need to know this for your MCQs. BD also they can represent, or they'll be giving it as O of E plus B. So how this is achieved all in your next ADA class you will learn. So the application of BFS is your navigation systems, GPS navigation systems goes from one to the other, find its nearby vertex, it moves on to the other. So if any problem, if you receive by means of GPS, apply this concept, BFS concept. Similarly, networks also, one system connected to the other, then from there to the next system, likewise, interconnectivity. Then your Facebook also, you know about one, your friend, you will be a friend of someone else, from there you will be a friend of someone else. So again, so but anyway, this person will have a link with this connectivity here, 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 also here, here. So likewise, that is what your Facebook. So everything is your BFS concept included applications. Okay, so these are the same thing only in explained manner I have given. Now I'll go with the DFS, depth first search. So till now we saw about BFS. Depth first search is from the name itself. It goes to the depth, to the last level, to the bottom level. Okay. So for the depth first search also, first thing which you have to find is, these are all the explanation. I'll tell you the explanation with the example. Then you will understand the previous paragraphs also what is being written. So, so now see here. If a graph is given, first take the adjacency list of the graph. Why am I? Oh, so because for depth first search, this adjacency list will help you a lot. Or if you could find from the diagram also, it is okay. But always it is better if you write the, when a graph is given, adjacency list you can find, or else when a list is given, a graph also you can draw, because both will help you in some manner to solve your problem. Okay, so in this case your adjacency list will help you a lot, because here we might miss some lines if it is a complicated diagram. We will be missing out some arrow marks. If you miss out, then our entire problem will go wrong. So it's better if you write the adjacency list, which makes you to solve it easily. So for each adjacency list I have written, see for A, it will be the adjacency outgoings, B, C, D. Okay, B, C, D. Then for B, outgoing is, nah, Sarat Sai is there. Sarat Sai.
Yes, ma'am.
Yeah, for B, what are the adjacency list for B?
Only E.
Why are you telling it is only E?
Because only the arrow is outward arrow from B is only to E.
Yes, okay, good. Good, good. Okay. Sanjeeva Kumar. Sanjeeva Kumar.
Yes, ma'am.
What is the adjacency vertex of C? Adjacency vertex of C.
Text of C. B, ma'am.
Uh, B, yes. B, only B. Why you are telling it as B?
C is pointing towards B.
B. There is only one outgoing. Huh? What is about then this then?
Incoming.
No, this one. This line.
G and also
Ah,
B.
B and G. Okay. So I think you can find out the remaining also. So C for B and G, and for then again D it will be C and G, because outgoing C and G. Then E, F, G, H, I. So find out the adjacency list for all of the particular nodes, and then what you have to do is do the depth first search algorithm. So here depth first search algorithm is another one. If they ask you to find from any of the node, you can find it, or else if they ask you to find, if they have not given any of the nodes to find out, go to the dead end, either to H or to this dead end. From A, go to the dead end and you can start traversing. Okay, go to the depth level of your A node, A's left or right, any depth level you go and start spanning from there. Okay, so that is the way you have to find the depth first search. Okay, so depth first, or else if they give a node, maybe they'll be giving it as find out the depth first search with starting node. See, the starting node, they can give it as any node. It is not the thing. They will always tell us to start from A. Okay, if the starting node is not specified, you can choose any node, but you have to mention that you are choosing the particular node as the source node. Okay, that is very compulsorily needed. So in this case, I have taken H and solved. If they are giving I, then you can take I, or if they are giving A, B, C, D, E, F, G, H, I is the last one. If I need to take from I, you can start from I also. So anywhere you can take. But here in this, as per this explanation, it is started from H. So that's what I told you. The spanning tree, that is your depth first search spanning tree, can be any starting node, can be any node. Even BFS also starting node can be any node. But provided from that particular node, you have to follow the concept correctly. So when I take H, now see here, I am pushing H inside the stack. So what I will do is, now listen here, if I, in this diagram, if I could tell you, it will be, I think it will be easy. Then I'll go with that. Okay. So now see here, H I am pushing inside the stack. Okay, what are the adjacency vertices of H? Look into this adjacency list and tell me what are the adjacency vertex of H?
E and I.
E and I. So what I am doing is, now when I found the adjacent vertex of H, I will pop the H outside. So that is push H into the stack, pop and print the top element of the stack, and then you push all the neighbors of H inside the stack. So now I will take H outside. Pop, I have popped H outside and I will push E and E I push inside, then I. Clear now? I'll push E and I inside the stack. Now, which one I have to pop? In Q, which one you will be popping? Which one you will be taking it out? E and I if I push. E only I will take out in Q. Clear? In Q, I will take E out and I will find the adjacent vertex of E. But in stack, which one I have to take out?
I.
I. So I will be taken out. When I is taken out, all what I have to push inside. So I is taken out. What I have to push inside?
F.
F will be pushed inside. Okay. Now, wait a minute. 527. 527. Now I'll going to call by roll numbers.
Ma'am,
Because name. Okay. 520. What will be my next step?
we'll see the adjacent
Yeah,
nodes.
before seeing the adjacent, what I should do? Before seeing the adjacent, what I should do? Adjacent is okay, but before that, I have to. In your BFS also same concept only, ma. You will NQ, you will take it out, and then you will DQ from the particular Q, and then you will push inside the adjacent vertices. Now F, when I take it out, what I should do before I push the adjacent vertex inside?
Pop F out.
So F has to be taken out, and I will be pushing what I should push inside. What I should push inside?
I and C.
Yeah. Adjacent vertex of F, ma.
C.
C and
Sorry, H and C.
C. See what order you have written here, the same thing you follow first. If you have written H and C, then H and C you can write. Now here it is C and H. So I will do C and H over here. Okay. See H, oh, 1 minute. Forgot. H actually you should not push inside. Why?
because
H
it's
is
already
already
there.
visited. Yeah, already visited. That's the meaning. Already taken out, visited. See, pushed in and taken out means that meaning is visited. Okay. So H I will not push in, only C will enter in. Now, 545. Who is 545? What is my next step? 545. Who is 545, ma? Naman Jain, what happened? Aryan Kapoor. Aryan
Yes,
Kapoor.
ma'am.
What is my next step?
Ma'am, we will say adjacent sides of D.
No, no. Here E is there, C is there. Now what I should do?
We will DQE.
DQE. Ah.
Yes,
This is stack, ma.
ma'am. And we will pop up C here.
C is, so C is now printing here, and now what should be pushed inside?
Ma'am, we will see the adjacents of D.
C is adjacency, ma. What is C is adjacency?
Ma'am, C adjacent. Ma'am, B and G.
B and
G.
which one you are popping out, that adjacency will push in if it is not yet entered the queue or if it is not yet visited. Okay, listen
Yes,
carefully.
ma'am.
I think many are still sleeping, I think so. So C you have taken out. So next one is B and G. Now G only has to be taken out. So G I will be taking out, and G's adjacency are F, H, and I. F is already visited, it is printed. H also already printed, I is also already printed. So next I will pop out B. B I will pop out now. Now B's adjacency I have to look E. E is already there in the queue. So that also I will leave it out. So next there are no more things, only E is there. So E I will take out. Clear? So this is the way how I print the, or this is the spanning tree from the node H. So that is what here. First you are printing H, then you are pushing I inside, then E and F are getting inside. F is popped out. F because topmost stack. F popped out. Then C is pushed in. So what all I have told here, the explanation is all over here. And finally, the output is here. So these are the nodes which are reachable from the node H. Okay, so this is also same depth time complexity. And application is detecting a cycle. If there is any cycle you can detect in a graph, that can be done by means of DFS, anywhere pathfinding solution. And here there is backtracking is there, because this is, since backtracking is there, then only we are going, see, this is what called as backtracking. When I took G out, if there are no more nodes, I will go behind. Then when I took B out, then again adjacent vertex of B, E. So there are no more nodes to be visited. I went below. That is what called as backtracking. Backtracking means you are going through one particular solution. So many streets you are moving to the left, right, second street, third street, fourth street, all the streets you have gone. Now we have gone to the fifth street, and you find there is no way to proceed from 5 to the next street. So what you will do, you will come back to the which street? I need the answer.
Fourth.
Fourth street. So you are traveling from 1 to 2, 2 to 3, 3 to 4, 4 to 5. When you go to 5, from 5 there is no 6. So what I'll do? I will backtrack from 5 to 4, and from 4 there is a 6. If still this is not there, I have to backtrack here to find out there is a way over here. Okay, so this is called as many puzzles you would have shown, you would have solved, right? If you couldn't get the answer, you will backtrack and find out. So that puzzle name is here maze. So solving puzzles with one solution. So backtracking is a very important concept which you will study in detail in your next semester in ADA. So whatever algorithm, few algorithms, DS is basic concept. If you understand DS well, ADA will be very easy. So here DFS is using a concept of backtracking. So anyway, DFS and BFS, once again, you will study in your next semester also in detail. Okay, but as of now, keep it in mind, DFS takes the stack concept, BFS takes the queue concept. And DFS, queue concept means first in, first out, whichever is entering first will come out first, and the adjacent vertex will be pushed in. And pushed in means it will go at the back only, not in the front, it won't be pushed. In DFS stack concept, right? So whichever vertex is before you push in, you are popping the particular vertex out and you are pushing inside the adjacent vertices. Okay, so this is what your application of DFS. This problem you can solve at home and see. This is your work. You can solve and see both the BFS and DFS. Find out both. So this is for your practice, this problem. Okay. And next topic is biconnectivity. Biconnectivity means a connected, see, this is a graph. All are connected to one another. If there are no vertices whose removal disconnects the rest of the graph. For example, see here. If I take out the D, how will F and E will be connected? It cannot be connected, right? It stands single. Okay, so the vertices, this you should know. The vertices whose removal would disconnect the graph only, you call it as articulation points. So when I take C also, I cannot, when I take remove C, then A and B only will be connected. You know, A, B, D, F, E can be connected, but there is no a solution to G. Or when I remove D also, there is no solution to F and E. But when I remove B, no, when I remove B, not remove C otherwise, what happens is even though B, there is a connection from A to B and C to B. Okay, so certain things where the vertices which you are removing, if it disconnects the whole graph, means that is called as articulation points. So see here, when I am removing C, this is left out single, but it has connection to D. Similarly, when I am removing D, these two are left out single. So C and D are called as your articulation points. Okay, C and D are called as articulation points. It is not the thing there will be only one or two. There can be many articulation points. Main thing is if you remove that particular point, if it disconnects the rest of the graph, then that will be called as your articulation points. Okay, so this is called as biconnectivity. I think hopefully you are clear in this topics, right? In this biconnectivity, BFS and DFS. Okay, so next is your minimum spanning tree. Okay, minimum spanning tree is very important concept in your fifth unit. Minimum spanning tree has two algorithms, Prim's and Kruskal's, and shortest path has one algorithm called as digit graph. Okay, so minimum spanning tree means it is a graph that contains many vertices and it is a tree also. So what actually you can do is when you start from a node, you span all the vertices, and but it should not form a cycle. Okay. So for this graph, the costs are given in the A to B 2 and A to D it is 8, D to C 4. Likewise, all the costs are given over here. So now I have to find out how many spanning trees are there. Okay, how many spanning trees are there? So as of now, I have told that 16 spanning trees. How? Now we can create the spanning trees. Now see here, A, B, C. I can go from A to B, A to D, A to C. This is one spanning tree, right? Spanning tree means like this. Wait, I will tell you. A, B, C, D. Okay. So what I will do is the cost also should be minimum. So first I will try out which is the minimum cost. Okay, B to C is having a minimum. So I'll put 1. Then again A to C also I can connect. Or A to B. Okay, A to 2. A to C is 2 only. Right? A to, yeah. And now D to C. How much is the cost now? All the
7.
vertices are connected now. But how much is the cost? 7. Do you find any other cost like this? There are so many values, right? You can do. That is what here. Now see here. The graph has 2 minimum cost spanning trees, each with the cost of 6. So I have taken all the possibilities I have drawn. A to D 8, D to C 4, C to D 1. So, and if I close this, then it will become a closed graph. It is wrong. Your graph should not contain a cycle. So what is the value for this, ma'am? What is the total for this graph?
13.
13. Next graph?
12.
12. Next graph?
15.
15. For this graph?
6 and 6.
6 and 6. One more thing, this also you can draw here. I have left that because 16 spanning trees, I have drawn only few. Okay, so 16 spanning trees, few only has been drawn. So, but our thing is to take out the, and here also, here it is 4, 5, 6, 7, and this one 4, 6.
Not 7, ma'am. 6.
This one, oh, here also it is 6. So, this diagram only is taken out here. Okay, fine. So, but this graph is also there, which you can add it over here, but that is anyway containing 7. So, ours is only 6 minimum from all the spanning trees, which is the minimum one I have taken. So, this is only taking the minimum cost spanning trees, but I have not applied, just I have looked into the, based upon the weights I have assigned, that's all. But how to find out using my algorithms. So, Prim's and Kruskal's are the 2 algorithms. Kruskal's is very, very easy. Prim's is also easy. It has some formula, that's all. Prim's is having a formula. Kruskal's is we will be ordering the weights and we will be finding out we will be just drawing the edges alone. So this is very easy to find out. This both will give the same answer only, whichever method you follow. But unless if they ask you to find the if they give a graph and if they ask you to find the minimum spanning tree, you can choose Kruskal's because it will be very easy. If they ask you in general, find out the minimum spanning tree for the below graph, take Kruskal's and solve it. In case if they ask you to do specifically follow a method for use Prim's algorithm to find the minimum spanning tree, means you have to do only Prim's. Okay, Prim's is also very easy provided there is a formula alone. The formula you have to be little bit careful. That's all. Otherwise, both are good. And if you know Prim's, digit cross is very easy. Prims and digit cross are related to one another, but the thing is, Prims will be having one digit cross is having one one vertex extra than, that is vertex not in a formula. One criteria, one parameter is extra than Prims. That's all. But procedure is exactly the same. But one main difference is there between Prims and Kruskal's. For Prims, you will be finding the cost of the spanning tree. That is, if a particular tree is given, you can tell that from the particular source node to the destination node, I can go through any way provided my cost should be minimum. But in digit cross, you are not going to find the cost, you are going to find the path. Path in the sense here, as when I take this diagram, I can reach here, that is an undirected graph. So A to C I can go, then C to B I can go, then C to D I'll go anywhere. Okay. So but anyway, if I start from A, I'm going to reach everywhere. Similarly, if I start from B also, I can reach here, then I can go here, but I'll return back. So there is a double cost over here, then I'll go here. So these are normally. But when I come to digit cross, what I'm telling is from a particular place, maybe from A to B, how much? A to C how much, A to D how much. This is only we will take it in digit class. Okay, that is from one particular thing to this. From one particular source to the